Hello, everyone. Welcome to today's webinar. My name is Khalil Doheny. I'm the Director of Content Marketing at Digital Niche Agency. Today we have Charles from Atombeam. Charles, how are you doing today?
Good, good. Khalil, how are you?
Doing great, doing great. Charles, do you want to introduce our guest here and then let's just get this rock and rolling?
Sounds good. All right. So we have today with us Brian Galvin, who is sort of a polymath and both a guy who's our primary patent agent, but he's also a data scientist. And he's going to be talking with us and today about a new concept. And it's an early stage development concept, but it's really, really cool. And it's called the Large Code Word Model, the LCM. And so we're going to be talking about that. I'm going to also give you a quick update generally on the company. And also, because a lot of folks have, sort of joined in here that haven't historically had, the lecture about data as code words and NERPAC and all that, we're going to talk a little about that too. Brian, if it's all right with you, I'll hold off on you introducing yourself until after I do a quick, necessary, warning to the world that, we're not raising yet and all that stuff. Okay.
Yep.
All right, here we go. So I am going to share. Okay. All right. Everybody see that properly?
Yes.
Okay, good. All right. So I'm going to read this quickly. No money or other consideration is being solicited, and if sent in response, will not be accepted. No offer to buy the securities, that is the Atombeam stock, can be accepted, and no part of the purchase price can be received until the offering statement is filed and only through an intermediary's platform. An indication of interest involves no obligation or commitment of any kind. Reserving securities is simply an indication of interest. And so just to expand on that slightly, if you have an interest in investing, again, there's no obligation. You just go to the Start Engine site and register your interest in buying some stock in Atombeam, but you're not obligating yourself to do so, just to be clear. All right. So with no further ado, let's do a quick introduction of Brian. I think most folks know me already, and so the brief introduction down there for me. But Brian, do you want to talk a little about your background here?
Well, sure. My name is Brian Galvin, and like Charles, I'm former naval officer. I was a nuclear engineer in the Navy, and it was career number one. And then I was in high-tech telecommunications software, ultimately became CTO at Genesis and then Nuance. And I have roughly 50 patents where I'm an inventor. So I sort of got into the patent business as an inventor, and I now, and for the last 15 years, have been practicing in patent law as a patent agent. So
right.
that's
yeah,
me.
no, and Brian is one of my brain trust. He is, when I was first introduced to him by somebody that I know from that knew me from business school, he said, "You've got to get Brian, hire Brian, don't even think about it." And I had been interviewing big law firms, and I said, "Really?" And he said, "Yes, don't think about it." And so I didn't. So it's proved to be a very good idea. Anyway, so good. So first, I want to talk quickly give some background here on the company, just so everybody gets a catch up. So first thing is we focus on IoT data with our first product, NERPAC. And the way you think about how much of data is out there, zettabytes, one with 21 zeros, gigantic number. And if every byte in a zettabyte was a grain of rice, it would fill the Pacific Ocean. That's so big. And then you think about, well, how many zettabytes next year? 90 zettabytes of data, 90 Pacific Oceans. That's a lot. And how much global storage can it be put into? Not nearly as much. And so you've got kind of a big disconnect between how much data gets generated, how big the pipes are to send it, and how much you can store. So that means that you need to do something to make it all more efficient. That's what it boils down to with our stuff. And so if you to add it all up, you'd say, okay, historically, legacy systems are focused on using and storing and so forth, any data on the basis of what humans need, which is a lot of context. It's a lot of repetition. It's a lot of things that, are just not very useful for a computer, but humans need it. And then when you use compression on it, well, you lose a lot of the value that you could get out of it because you can't do anything with it until you decompress it again. So what we do really is with our systems is we take all that stuff, all that extra unnecessary stuff, and we squeeze it out. And we're doing different things to make it more valuable, make it more usable. All those things mean that we have not only making it smaller, but it's more secure, and we're allowing access to it for generative AI, which is what Brian's going to be addressing, because the smaller data is still useful. That's the key thing. So quickly on the products we have. So the first one that's now released as a product, and it's undergoing testing with several big companies right now, NeurPack. 4 times more bandwidth on average, adds security to it, and is searchable. NeurComp, that's under development still with the Air Force. It's still in mid-stage development, lots of really good progress. We're still getting paid for developing it. And that's looking very good. And finally, the large code word model. And that's what Brian's going to be talking about in his chunk. And really, it comes down to thinking about data instead of, like, again, in the human contextualization, thinking about data as code words. And I'm going to talk a little more about that. But really, when you think about it that way, you could get more efficiency. You can get access to all sorts of other kinds of data than just text, which is what LLMs do. I mean, Brian's going to talk about that, how important it is, and potentially autonomous learning. So now, if you were to talk about, like, what I want to address here is data as code words. So here's an IoT device. It's a swimming pool thing, right? And it says and this is all in human words up above, and then down below it's in binary, right? And that's the same thing except in binary. And then when we say, okay, now what we do is we find patterns in that binary. That's fundamentally what NeurPack does. And everything from that flows from that concept. And the way we do it is we build code books. Now, the code books look at thousands and thousands of these little messages, and it uses machine learning, kind of AI, to do that. And then it's looking in the payloads for patterns. And when it compares across the payloads of thousands of these things, of these little messages, then it can find patterns that are used frequently and puts those patterns that it finds. They might be 64, 128, 200, all sorts of different sizes. It puts the patterns into a code book and assigns each a code word. So you might have a 128-bit pattern represented by a 3-bit, 5-bit, 10-bit code word. And so that basically squeezes down the effect of the amount of data that the computer needs to look at a lot. So instead of having to look at 128 bits, it looks at 3 bits or 5 bits. And then what happens in runtime, that is to say, when you have a computer doing things in the real world, say it's that temperature sensor thing, it generates a message. The payload, that is to say the information in the message, is chopped up into whatever the pattern lengths are, and it's swapped out for code words. That's all that's happening. And so it's a really fast, light thing. And so that reduces the size by about 75%, but it does it almost instantly. And now when you have both sides of a communication, that have the same code book, and they can do this kind of lookup process. Now they can communicate on average about 4 times faster than you could before. And you can't use compression on little tiny messages, because the compression will add a big old header, and then it won't find much to reduce, because compression relies on finding duplicates of patterns within a message, whereas we're talking about finding duplicates of pattern out of our code book. It's a major difference, and it gets a lot of interest. But the key thing to think about for purposes of this discussion today is the idea of data as code words, and how a computer, to the computer, what does it mean? What is this 3 bits or 10 bits code word mean? And to a computer, in this case, you have a 4-bit code word, and to the computer, almost instantly, it can see and use the 128 bits that is in the pattern. Now, this is just an example, right? And these vary, 3 bits, 10 bits, whatever, code words, and the patterns vary in size too. But fundamentally, if you were able to, if you're a computer, you can see through this using NERPAC with the associated code book. You can see that pattern just as easily as you could see the original data, or almost as easily. I mean, it's virtually the same. And then just to quickly touch on NERCOM. So NERCOM is in development again. It's not a released product, but we're making really good progress. And when you compare it to what it is it's a very advanced kind of AI combined with a standard video codec. And so when you compare it to how just a standard video codec how much reduction it would get, which state-of-the-art codec, it gets about twice as much reduction. So you can send twice as many images through the same pipe. Now, that's a really, really big deal, but it's not a commercial product yet, but it looks really promising. So just really quickly on where we are with stuff, our big focus at the moment is like on the DoD side are this work we're doing with the Air Force and the Space Force. Both of those are proceeding really well, both of those contracts. And we have strong encouragement coming from the Navy, as well as especially from the Space Force, to proceed on some additional work with them. Lockheed is continuing to want to work with us, and we're waiting till we get a little further down the road, because they would charge us money to be a subcontractor to us. And so we're trying to hold on to our money, right? And but at the same time, we definitely, all I have to do is say, hey, we're ready to go, and we would be working with them. Ericsson has a big division, like $1 billion division, that makes gateways, which are the way that gather up data coming from a bunch of sensors and send it somewhere. And they're, I don't know if they're the biggest, but they're one of the biggest, Cradlepoint, their division. That division is working with us right now, because the way our go-to-market works, and the same is kind of true with Viasat through some of its manufacturers. The way it really works is, if BMW or Chevron or Exxon Mobil or whatever, if those guys want to work with us, they want to buy a box that then they install somewhere. So that makes it necessary for us first to work with Cradlepoint, or, you know, a satellite terminal maker or whatever. First, get our stuff working smoothly and everything with them. And then the net is it gets bought, you know, those boxes get bought, tested, and so forth by the big end user customers. And those big end users, you know, want a finished product. They don't want to like have to do any installation or stuff. They want to buy a box and stick the box in and pay whatever it costs. So that makes it longer for us to go to market. That's why we're not, boom, selling rate day one. But, you know, in the fall, we will be, I believe. And then here's our here's various partners we have. Mentioned some of them. I think we're being very cautious with a lot of them because big companies like to take your stuff, and that's one of the reasons we're so focused on patents. But we've got a lot of interest. And speaking actually of patents, we have 48 now that have been issued or allowed, and there's another 50 that are pending, thanks to Brian and our internal brain trust. We've got some serious chops when it comes to generating all these patents and really putting up as strong as we can, walls against potential infringement. There's no guarantee we will be able to defend it, but we even have some ideas about how we would fund a process if it came to it. But as of right now, we don't know of anyone who's infringing. But if anybody hears anything, sure, let me know. So with that, I want to turn this over to Brian and have Brian talk about what we see as potentially the next generation of generative AI, which is focused on the idea of data as code words. So, Brian, do you want to take it from here, please?
Sure, absolutely. And I'll give you little cues when you need to move the slide.
Well,
so there's a bit of a disclaimer here at the bottom of this slide that's worth briefly mentioning. So the LCM, or large code word model, is in a very early stage of development, and it may not prove as viable as a product as we hope. It may require resources beyond the capabilities of Atombeam, and it may not prove to be competitive in the generative AI marketplace. Certainly, for example, as a replacement or a competitor, direct competitor with Google or OpenAI and so forth. I mean, it's not necessarily going to be that. Very likely not going to be that, but it's early stage. We don't really know what it's going to look like when if it gets to it being a product. What we want to talk about today is some of the conceptual underpinnings, some work we've done to date, why we're excited about it, and where we think it can lead. So if you want to click there, Charles. So as deep learning or machine learning or AI, all these words sort of munge together, but everyone's familiar with ChatGPT and probably familiar with Gemini from Google and Claude and so forth, the co-pilots from Microsoft. So generative AI in the text world is very well known. It's very front of mind for everybody. There's also, of course, generative AI in the image world, such as diffusion-based models like Midjourney and so forth. So there's a lot happening, but it's part of a general reality that's happening, which is as the scale of deep learning architectures grows, both in terms of the complexity of the core, which is the thing that gets trained. So your core of the ChatGPT, Gemini, Claude, they all use what's called a transformer core. It's a very complex neural network architecture that's really good for modeling language. And it's the sort of the core idea that is used to build large language models, or LLMs. And there are other cores like the diffusion model for images and so forth. But as these technologies become more advanced, both in terms of size, but also sophistication, because the human learning is taking place at a really rapid pace, these smart models are dealing with abstract data already. So one of the key sort of things for us as we're thinking of data as code words is to say, well, why not train deep learning models like a transformer, a large language model, or other ones for images or time series or whatever? Why not train a model using code words? Rather than sending code words or having code words in a data lake somewhere and pulling them up and then turning them into data and then training the model on data, train the model on code words. This is sort of happening already with LLMs, although they're not using code words, but with LLMs, they're trained using things called tokens, which are actually really small chunks of text, including spaces and punctuation marks. And these chunks of text would not really be recognizable as words or even having any semantic meaning because they're small, like CA is a token typically, not CATS. So LLMs are built, they're trained using tokens. So something like 500 petabytes of text data from everything under the sun, the entire internet, all the books that have ever been printed, et cetera. I mean, this is well-known information, are used to train these large language models. But before those documents, those text data sources go in, they get tokenized. They get turned into a stream of tokens. Well, a large code word model skips right down to the bare metal and says, let's just send tokens, code words in. So what if you train the model on code words natively? Is sort of the beginning of what has turned into a very fruitful investigation at Atombeam. So if you use code words, and we've actually done a tiny proof of concept where we built a tiny language model, or I should say a tiny code word model. We actually built the same model trained on just one thing, War and Peace. So we built one using tokens, and we built the same thing using code words, and they both work. So essentially, if you're using code words in an LLM world, it has actually a very good advantage, even at that sort of early stage, is that you could take a complicated prompt at a browser or an API endpoint somewhere out on the internet and turn it into code words. So now you transmit it over the internet, and it's secure and it's small. So you get, a big reduction, 80–90% reduction, maybe if it's text, but it's a substantial reduction regardless in the size, but it also is secure, and that flows into the cloud. And then instead of converting it back into text, those code words go directly into the model, which has been trained on code words. So in the case of a large language model equivalent, you'd take all that text data and you would turn it into code words. You'd store it as code words, and which would be much smaller, and you'd train the model on code words natively. So LLMs use tokens. They're trained on a large amount of text samples, and people are familiar with ChatGPT, Gemini, Claude, et cetera. LCMs, large code word models, use code words. They're trained on code words natively, and that's important also because it doesn't sound very different or earth-shaking maybe when you're talking about LLM versus LCM directly, but an LCM can also take financial data, which is numerical, or image data, or any kind of data, and once it's turned into code words, i.e. it's compressed and it's in an abstract formulation, those code words can be used to train a model that is natively multimodal. So you can feed code words in. The model doesn't know whether it's text or whatever. I mean, how you feed it in will depend on what it is, but that's true of every modeling system. You just have to start by preparing your data. But the actual core thing that gets trained and that then does stuff for people like ChatGPT, it doesn't know what those code words really represent any more than a language model knows what those tokens really represent. It just looks at the sequence of tokens, or in the case of an LCM, the sequence of code words. So that's sort of the first core idea of LCMs, is that these are models that are trained natively using code words. If you want to go to the next slide, please, Charles. So that actually leads to a lot of interesting implications or results, consequences. So if you compare current generation generative AI, such as ChatGPT, and you look at what we envision for an Atombeam large code word model, then on the one hand, as we mentioned in the previous slide, ChatGPT or any of the others uses language as its raw material. Atombeam's large code word models would use code words as their raw material. Efficiency, the really large models are very inefficient. I mean, they're always making them more efficient, but they're very large. They take a lot of resources, both time, compute power, and money, to train them and then to run them. With large code word models, they will tend to be less, sometimes dramatically less. And we're sort of working simultaneously on thinking of ways to rethink the core, the sort of learning architecture in the middle. If it's going to get native code words at the beginning, then maybe we can make it sort of more generalized. But also because now it's much less expensive to get data from wherever it is to the model, into the model, and to take the output from the model and use it, because all of that is done with code words. It's compressed, it's secure, it's fast, etc. large language models, the current generation, they're all announcing various multimodal features, but they all are still language models. So multimodal means I can take a picture and use it as part of my prompt for an LLM. And what happens is that picture will be pre-processed and turned into some text. And that text plus whatever you typed in as your prompt will become the augmented prompt. And that goes into the language model, which is expecting to receive streams of language tokens. And it does what it does. It generates a response, which comes out as a stream of language tokens, which may be code or markup code that could be shown in a browser as a pop-up window with a slider bar and some images. That looks and feels like it's multimodal, but the actual LLM is still taking language in and putting language out. And with
the difference really is just, sorry to interrupt, but to really make it crystal clear, what we're talking about when we say multimodal LLM is really your pre-processing and post-processing, but the core thing is still doing the same thing as it always does, which is operate on text, on language.
Right. So you can turn stuff into text and take it from text and turn it into something else, but the model is running on text. With a large code word model, it's sort of inherently multimodal because it doesn't really know or care what the code words are. So for instance, you can feed it a stream of code words that represents some textual data and some numerical data. And you train your model on that mixed data natively. So it's trained using multimodal data. LLMs are trained only using language. The other stuff's all pre and post processing, but the core is trained on language. A large code word model is trained on code words, which could represent language. They could represent financial data. They could represent meteorological data, medical data of various types, and so forth. We'll talk more about some examples. And finally, LLMs, it's a very big project. Like right now, I believe OpenAI is training up ChatGPT or GPT 5.0. That takes months and it costs a ton of money. And then once it's trained, it gets tuned and so forth, but it's set. And then you wait for the next big generation. And a large code word model is more naturally amenable to things where it's continuously learning. And it's trained on code words, and a lot of the use cases will involve making predictions and then comparing what actually happened to the prediction and tuning the model on the fly. So if you want to go to the next slide, Charles. Oh,
sorry. One more quick clarification on the last thing, because I think the autonomous learning, to the extent that it turns out that we can really do it, would be a big deal, because you would be to think. Let's stick to the medical thing for a moment. So you take, as part of, let's say, your ChatGPT and your OpenAI, and you're training ChatGPT 5.0, and you're going through and taking all the medical journals and pumping all that data in there. But then 3 months later, there's a bunch more medical journal articles out. So in both cases, I presume that you could add those in, right? But that's different from the autonomous learning that you're talking about with the LCM. So if you wouldn't mind expounding on that a little, I think that would help.
Well, yeah. So the idea is that a large code word model can be. We haven't done this yet, but this is one of our ideas for where we go with this. Is that you can train a model so that it. For instance, let's take the medical example. It is trained on all the medical data we can get for it. We're talking EKG data, we're talking image data, a lot of imaging in medicine, of course, X-rays, CAT scans, etc., MRIs, all the medical journals, all the patient notes. Obviously, there are privacy issues, and this may be done sort of by a hospital. We haven't, we're not dealing with the reality of this yet. In reality, there's a lot of issues about privacy, anonymization, but those are all issues to be addressed when we're further along. But fundamentally, you take all those kinds of data in, you train on all that, and then you say you have such an LCM operating in a clinical environment. A patient presents, there's data coming from all the sensors, there's lab results coming in, there's notes being taken by physicians and PAs and nurses, and then then there's all the background stuff, that's already out in the medical world, the journals and so forth. And as this patient is treatment sort of scenario is evolving, the system may predict things, and it may provide diagnostic assistance, treatment recommendations, and then things get done, and the patients react, and more data is generated, and that data it's compared against the predicted data and the desired path of data and so forth, and adjustments can be recommended on the fly because the model is essentially autonomously learning. Now it's learning about this patient in this situation right now, but it's learning from a natively multimodal set of data, obviously represented as code words. The multimodal meaning I've got data from electrical sensors, devices, medical devices like CAT scans, MRIs, EKGs, even the thing on your fingertip that takes temperature, and it takes pulse and blood pressure, and can measure your blood oxygenation and so forth. All of that creates a lot of data that's all going to the model, and the model can adjust on the fly as this patient's situation develops. And then, of course, in contact with many, many patients, once these things are deployed widely, then all of that learning feeds up in a federated way to sort of the whole system. So everybody benefits from learning in the field.
So why should we care, though, if you're trading and operating on, pictures that are converted to text, and then versus you doing the same thing on code words? Why is this a big deal, to, compare those?
Well, so if you're doing with an LLM only, then if you're converting everything to text, it's very hard to predict time series data with using words. For example, it's very hard to identify defects in an image, or like medical problems in an image, using words. So that's why people don't use a large language models to generate images. They may use a large language model to interpret a request that then goes to a diffusion model that generates an image per that request, but they don't expect ChatGPT to generate an image from scratch. And it can't do that. It can generate words. So by training a model on the multiple kinds of data, then the model is already, it probably won't look, the inside of the model won't look the same as current LLMs, because if you're dealing with data that comes in sort of time series, and data that comes in XY grids, which are images, and data that comes in language, what you want is a model that can receive data of differing kinds as code words, which is just an abstraction layer, and then be trained on a large amount of data. So in principle, you would train such a model by feeding it lots of medical imaging data, lots of medical device output, lots of patient notes, and of course you have to correlate these things. Another example is with financial. You could have all the news feeds coming in to a large language model, but if it doesn't also have the financial ticker data, which is numerical data coming in, and if you can't align those in time, so that that certain phrases or things happening in news are likely to have certain effects on markets, and in fact the model may have learned that certain kind of news, like disruption of oil supply in the Persian Gulf, is likely to lead to a short-term transient in oil price, and a look-ahead transient in interest rates, which will tend to go up. And it may predict that there will be a short-term reaction, but that short-term reaction will be mitigated by whatever the actual output of the oil news is. Well, all those kinds of data are coming in and being trained on at once, and that's something that just can't be done with an LLM, because they don't, for one thing, have a sense of time. They just receive a sequence of tokens of text, and based on that sequence, having been trained on, we'll just be simplified and say all text, all the text that's ever been fit to put on the internet is been used to train these models. So it can receive text, and it can generate really excellent text, but it can't predict the time series, especially further out, or it's one kind of problem. The idea is to of LCMs is partly to make LLMs more efficient, So that's sort of an early stage goal, but also by making natively multimodal models, and have been examples, the medical and the financial. We're getting data of 2 or more different types, all represented as code words. And of course, there's a lot of work that goes in the preparation of that data so that the model, when it's getting trained on this data, will learn in a way that makes sense, because you'll have financial data and related textual data more or less aligned in time when it's fed to the model. So the model learns that there's a correlation in time between such and such happening in the sort of blogosphere and the news sphere and on Twitter or X and so forth, and movements in the markets. Same thing with medical, with weather. I mean, it's pretty general. The idea is to be sort of a next generation of sort of deep learning architecture.
Right. All right. So here's speaking of medical.
Right. So this is the example we were talking about earlier. So right now, if you really wanted to have a machine, just think about a black box, an AGI kind of box, artificial general intelligence. So you want to be able to feed it all the research papers, all the clinical research data, everything done in a clinical trial, all genomic data, proteomic data, et cetera, bioinformatics, doctor's notes, images, radiology, but also all the lab reports, all of that information. You train a big LCM on that kind of data, whether you're doing it for one hospital system or you're trying to build sort of an LCM that absorbs all that data from all sources. But you train that model, and then from that you would in principle be able to make new causation predictions about diseases. You might find a correlation of something happening in 2 or 3 unrelated things that wouldn't be connected, are found to be reliably predictive of disease X. And you can also get new therapy ideas, predictions, there is already a lot of work going on using AI for drug discovery, for example. Having all this information available can feed this. Now, if you think about a large language model today, if you want to go ahead and click your button there, a large language model wouldn't typically have most of this data ready at hand, because it won't have image data going into it. You don't train an LLM on MRI scans. You don't train it on proteomics data and genomic data and gut flora, genetic data and so forth. So it only has doctor's notes and research papers, and whatever portion of, say, clinical research data is in text form. In a similar way, if you want to go to the next slide, the financial example. Oh no, I'm sorry. This is the fighter aircraft. So a really big effort for the last 20 years in the defense world is to have smarter airplanes, for example, that you can think of an F-35 as like a flying sensor package. So a lot of data is being absorbed. And if you had all that data in hand and you used all that data to feed a model, and not just that data, but data,
right?
What's that?
Time. That is to say, while you're in like an actual dogfight.
Well, not yet. That's using the model. To train the model, you take all this historical data and you train a model and you train it on everything you know about any likely adversary aircraft and intel analysis, the results from adversary pilot training, if you had access to it, behavior that's observed now. Well, that's more real time, but you feed all this type of data into a training, and you train a model, which could, would be an LCM. It's another example of an LCM, because all this data would be represented as compressed, secure data in the form of code words. Obviously, there are dictionaries to turn it from code words to data that you can use in the real world to fly a plane or to help a pilot to think. But in order to have a model that helps a pilot in real time, so now we're using the model, understand what will the adversary do next and what's the best thing for me to do next, or even how do I get to where I want to go flying low to the ground without hitting things. There's all these different very complex challenges in advanced aircraft. To do that, you need all these kinds of data. If you want to click again, Charles, but a lot of that data is thank you. A lot of that data is numerical data. And also a lot of that data isn't available at training time. And so you need to be ingesting data and adjusting the model. So this idea of it's not the idea of having an intelligent model that plans and then reacts to my plan's not going the way I want is not by itself new, but the idea of thinking more generally about training models natively on code words and training them in a way that's more natively multimodal and training them for a wider range of tasks, including prediction, and then you compare the prediction to what we planned. So prediction and planning are two sides of the same coin. So in the case of flying an aircraft, I'm predicting what the adversary might do, and including what people on the ground might be doing. And I'm based on that planning what are a logical set of next steps for me to do, the pilot and the plane. And then things are going to happen that are going to differ from the plan, and it's going to adjust those on the fly. That is not a natural LLM use case, but it is, and this would be a very advanced LCM. So, this isn't going to be around anytime soon, but this is the idea of behind the core concept of LCMs, which is training deep learning models on code words natively so that it becomes easier to train natively multimodal models and to train models with different kinds of data at the same time, so that, because for many real world use cases, you want numerical data that is, for instance, data reflecting the operation of an underlying complex system. So it's nonlinear data, it's got a lot of chaos in it and so forth. That's its own big challenge. And then we have language data, which maybe is all the chatter that goes on during a complicated flight between the guiding planes and the fighter planes, between the fighter planes and each other, et cetera, and all the historical data. So there's a lot of relevant language data. A large code word model for a given use case can be trained on the wide variety of data types. They're all presented as code words. And then it can, having learned, then it can operate in the real world, and it can carry out a wider range of very complex use cases in a sort of natural way. So we think of it as a sort of a next generation. I mean, think about if you naturally blended the capabilities of the diffusion model for image generation with the natural language understanding of an LLM. Right now, I can send a prompt to a diffusion model from an LLM and have it generate a picture, and I can call that multimodal. But what I really want is sort of a single model that has been trained, and it may use aspects of, because the diffusion model and the transformer model of LLMs are quite different on the inside. But people are continually, including us, are continually thinking about more general purpose cores for deep learning that aren't so tied to specific kinds of data and specific kinds of use cases, such as text data and sequence to sequence use cases. That's a large language model. We want something more general that can operate more robustly and more efficiently.
Yep.
I think that was the last slide. But want to
yeah, it is. It's just the other one's just a conclusion sort of thing.
Right. So yeah, go ahead, Charles. Back to you.
I was just going to say so just to be clear, we're having, as I said, as Brian said, this is really, it's early and it's exploratory. And the only reason we can talk about it is we have a few patents already filed around the basic ideas. Brian hasn't gone into some of the hows here, nor will he, nor should he. But I think the thing to realize here with the LCM, just net, is that by being able to take in and sort of understand natively time series data and merge it with, and time series data is something like what I was showing you earlier with the with that pool sensor thing, right? And so click, and here's the temperature, here's the humidity, and here's the time, and so forth. Then you can draw upon that and say you had a bunch of other environmental data and this, that, and the other. The LLM is a static thing in the sense that you train it up and it knows what it knows. And if you train it more, then it will know more, but it's not going to learn on its own. And it doesn't have any sense for, this is something that's happening over a period of time. And what happens when this happens, and then that happens. It's all to the LLM, all the same. Is that correctly characterizing it, Brian? You agree?
Yes, to an LLM, it's all going to need to be language input, and then it'll be language output, right?
Right. And so, so the big deal here is the multimodality and the ability in that multimodality to be able to understand time and to be able to, we think, and again, this isn't proven, to be able to understand from that there is an evolution of things that will occur over time. And because of that, because of that evolution of things, because it's going to be able to put together different things. Let's say, what's the price of Apple stock next Friday? Well, it can make a prediction. And you couldn't really, with an LLM, in any sense, really make a prediction. You can make a general prediction, but it's not going to learn, okay, I didn't think of that factor, and here's this new thing, and here's this, and be able to draw upon essentially all the information that we have everywhere, and to be able to correlate them together and draw conclusions based on the flow of time. And that's where the LCM becomes this possibly revolutionary thing. But it's all sort of goes back to the beginning to think about the general idea of code words and how code words, because computers can operate so fast, and because of the idea here of the code book, the idea of how little things in data can represent big things in data and almost instantly, then you have something that here that really could sort of pull everything together in the sense that here's NERPAC and here's what it does, and here's how it changes the way data is moved back and forth. But it also affects how data is stored, and so that you actually have access to it, you can see it, you can do things with it. And by the way, the thing that is probably, if it works, the best possible thing is this idea of this being able to place generative AI on top of that and access it all and use it to its greatest potential. So that's why, I was so excited about this thing. I'm calling it the big thing. But, again, as I say here again, it's very early, and Brian is building prototypes and filing patents and all that, but it's still, early stuff. There's a lot of stuff that absolutely we believe will work, but we haven't, till we prove it, it isn't proven. And just quickly on where we are on the, to be clear on, because it just occurred to me, I hadn't mentioned it, is why aren't we live now in the freaking offering on Start Engine? And the reason is, again, the SEC came back and said, well, we'd like more information about X, Y, and Z. And it's not a big deal. It's just a couple of things. And so we've already generated my part of the response. Now we just need to beat on the lawyers to do theirs. And so we probably will resubmit it from tomorrow. The lawyer's not around, but we think we'll resubmit it, and then we have another 10 days to wait for them again, assuming they don't respond earlier. But at any rate, so that's the holdup. I'm as frustrated as probably as anyone, or probably more. But the net is that I wanted to give everybody a quick update on where we were. Now, Cleo, I messed up here and we've taken too long, but give us some questions.
Yeah, there's a good amount of questions, so let's just try to go through these as quick as possible, and then whatever.
And Khalil, send me any of the questions, please. I'll do my best to get everything answered.
We'll do. All right, so the first one here is hoping Charles can talk about sales progress of SaaS before getting too deep.
Right. Yeah. So progress on the SaaS. So the SaaS is, as I've said before, it was released in April. What we're doing right now is there is, and we'll be announcing this probably, I think, in the next week to 2 weeks, a deal with Ericsson that it basically gives us And we've already shown it work, and they're happy with it, and it's not like a big experiment, but to make it enterprise level scalable and all that requires some extra stuff. And that's basically what they call the production side of the business. The R&D side is separate, and that's what Brian's working in, and like Josh Cooper and so forth. But the production side is the day-to-day, grind it out, make it into a real product thing, which in terms of resources takes a lot. And one of the key things you need in the context of that is to get is moving from a here's a really cool thing and it works and all that, into this will scale up to thousands, millions of devices. And that is hard to do. And that is the thing that we're working on now with, I think we will soon be formalized, I think, with Ericsson. But there's also others. There's a company in Singapore called Add Value that makes terminals and is one of the biggest terminal providers to Viasat. And next week I'm going to be speaking at Viasat, or actually we're doing a demo and a speak, and we're having a big meetings with top people there and all that stuff. They're very keen on what we're doing. So it's a matter of lining up with these partners so that anything that we need to do to make this scale, and because these guys don't want to hear that, we can do, a few hundred units. They want tens of thousands, and quickly, and no fuss. And the end users are, we were at this conference last week, IoT conference in Santa Clara, the biggest one, I think, in the US, at least. And we were mobbed nonstop, 270 leads. There were, people at our booth all the time. There's no question that we're going to have lots of interest, and I think personally, lots of customers. We just need to deliver the product to do the work it takes to scale it up. And that's where we're at. And it's not quick. That is the big focus of most of the people in the company, but it's not a fast thing, just to be clear. And that we can talk all day long about things that, are cool and work and all that at small scales and so forth. But ultimately, products are things that scale.
And what has to happen for Viasat to start generating revenue? And the same question for AWS.
Right. So with AWS, we need to go into their marketplace. And again, same thing. And it's the same thing with Viasat. We need to demonstrate that we can scale at enterprise levels. And yes, does it work? Absolutely. We can show it. And that's what we're going to be doing next week at Viasat and so forth. But a lot of the work you do is to be able to work hand in glove with a manufacturer of these devices. And that's what it takes to get ourselves really able to say, yeah, okay, Viasat, bring it on. And it's really mostly their distributors that would be selling it. We have no end of interest from distributors, but it's scaling up that product, making it into enterprise level. Same answer, basically.
And then are there concerns with patents OpenAI may have in place as we move forward with Atombeam LCM development efforts?
Right?
Well, I can't really talk about any particular legal work that I've done. On that side, I really can't say much. But as in general, OpenAI is emphasizing openness and doesn't have a lot of patents. But this is the LCM is sort of a very much in the research stage, and so we haven't done any extensive patent clearance operation, and I don't think we would find any problems because we're doing sort of new, different stuff. But it's early days, and so that I don't really have an answer to that because it's a little premature. I think you're muted.
Yeah. Talking about learning, how long does it take a system to learn?
Again, we're so early in it. I mean, we've
Talk
only
about LLMs versus,
well, yeah. So in principle, the training process for an LCM doing an equivalent job to an LLM would probably be maybe 50% faster, because you're sort of your data handling is lighter, but the inside of the model, you don't get as much of a bang for your buck in the current architecture of using code words versus language tokens. So there would be, but it would depend, in terms of how long does it take to learn. That really depends heavily on what you're doing, how big your data set is. I mean, if you're trying to build a competitor to OpenAI, which I'm not suggesting that we're certainly not doing it. I'm not sure we ever would do it. But if you did, you would take, a commensurate amount of resources to build the model with 500 petabytes of language, even if you've got that language stored in code word form, which will help you on input and output and so forth. But it's too early to say, but in general, we expect training times to be lower. And especially if you
but
build
talk about how
engines that are
long it
optimized
takes.
to work with code words, then a
Right.
lot
How
lower.
long does it take to train like ChatGPT 4?
About 5 months, I believe, several months.
Yeah.
The ChatGPT 5, the one they're training right now, I don't know how long, but I'm sure it's measured in months.
Right.
And then is the plan for the LCM to output in multi-model formats or text or one format only? The advantage of a multi-module input makes complete sense. It seems like a lot of additional complexity to output multi-module as well.
Multimodal.
Multi.
I'll answer that, Charles. So, you moved it over there. I was reading it. That's all right. Just go over there and then I can see it. Okay, so there will be a variety. I mean, right now it's all, we're doing proofs of concept and they're fairly straightforward, fairly simple, but the use case, for instance, of medical we talked about, the output there would be multimodal, and because you would probably be doing predictions. So let's say financial, you have sort of the ticker, you might have a UI that shows the predicted future, near-term future, and also some words and some alerts. So I would expect natively multimodal output as well. But in any deep learning, you're going to have data pre-processing, the core, the thing you've trained, and output post-processing. So if we train a model that is natively multimodal, because we've trained it on, say, time series data and text data together, then it'll be ingesting time series and text data out in real time, and learning, and since it's been trained, it will be producing output, which would presumably be a text time series graphic, probably in graph format or something, and words, but like everybody, there'd probably be an API, and you could connect it to the Bloomberg trading desk or something. So it would depend on use case, but in general, it's anticipated that an LCM that's trained multimodally, natively on multimodal code word data, would be able to provide truly multimodal output as well. But you may still do post-processing afterwards.
Awesome. And then Charles, I know we are running out of time here, so I will forward you all these questions. Is there anything you want to leave the audience with before we sign off here?
Yeah, well, very quickly, first, I would emphasize that we are earning revenue from the government. And that's real happening. That making this product, this, say, NERPAC, getting it into scalable, like we could sell smaller units now, right? That's not hard, but what we really want is to score the big points. And so the focus is on this heavy duty productization scalability thing. And so while it's not quick, I think I feel very good about where we are and how fast it'll scale once it's really at that point. I would also say that with respect to the capital raise on Start Engine, that everything is cool. It's just slow. And so, you know, the SEC actually was required to take 10 days and they took 12. But whatever, you know, so I can't do much about it other than to tell you we're not letting any grass grow, and it should be available, we think, within a couple of weeks, but it depends on how fast the SEC goes.
Awesome.
But in any case, thanks very much to everybody for investing, for being part of this. It's an exciting journey, and I believe we can change computing at a very basic level to make everything. I mean, really, this is the new generation potentially of computing. And, you know, if you put it all together and you say the hyper efficiency, the extra security, and put generative AI on top of that, that can access everything, now you're talking.
There we go. Thank you, gentlemen, for taking the time out of your days to talk to us. And thank you, everyone who attended the webinar. We will be posting a recap of the webinar on the Start Engine page, so be on the lookout for that. And
it
Charles,
will be, and importantly, it'll be on our YouTube channel.
yes.
It'll be on the Atombeam YouTube channel as soon as we possibly can do it.
Yep. And yeah, we'll be answering the questions that we couldn't get to today. So I hope everyone has a good rest of their day.
Great. All right. Thanks, everybody.